Hi, in this video, I'm going to go through chapter 7 of the Grokking Deep Reinforcement Learning book from Miguel Morales. In this chapter is an extension of the previous one. The previous one, we saw how we could improve the behavior, the policy of agents through different algorithms and make the comparison between them. So we saw SARSA, first visit Monte Carlo, Q learning, and double Q learning. And compared, we saw that most of the time Q learning and double Q learning were the best. Double Q learning didn't offer like a significant advantage, but Q learning was the simplest and more effective. So in here, we're going to introduce 4 additional algorithms to that improve the performance, but mostly it's the same. So we're going to introduce the SARSA lambda, which is an extension of the SARSA, and also the Q lambda Watkins, and that is also both of them are using the tracing technique. I'm going to talk more details about it, and then also we're going to introduce trajectory sampling and Dyna Q, which are model-based algorithms. So we're going to see how those algorithms are more efficient, more precise. Okay, so let's go to the code. I tried using Google Collaboratory, Jupyter Notebook here, but it crashed, so I was not able to. But I'm gonna just go through a source code. That should be enough to examine the results and do the comparison and also see the differences of the algorithms. So this is the last chapter in classical reinforcement learning algorithms. And the next, from next chapter on, we're gonna go through the use of deep learning and reinforcement learning, which is what is new. So these algorithms are quite old. One of them comes from the late 80s, and others come from the 90s. And some of the people that develop these algorithms are very influential in the artificial intelligence field. You can see more details about that in the book, which I highly recommend. So the initial part of the code is basically the same as last chapter, chapter 6. I recommend watching that before going here. And yeah, so it's basically importing the libraries, imprinting, getting the optimal value function, and pi, and optimal pi, and optimal q for as a baseline, and then just printing out the policy. You can watch the previous video for more details on these helper functions. They're identical. In this video, they're gonna use Slippery Walk 7 and Frozen Lake, which were used in the previous chapter as well, and that allows us to compare against what they had before. So, but also is using a more complicated environment called Frozen Lake 8x8, which is just a bigger version of the Frozen Lake. Okay, so this is the exploration rate and learning rates is the same. This is the same. We're getting the optimal value function, optimal Q, optimal pi. So let's go to SARSA. Before going to SARSA, I wanted to show you a couple of images from the book which explain the tracing technique, which the SARSA and SARSA lambda and Q lambda are using. So let's go to the first version of it, which is the accumulating traces. So the idea here is try to have a delay learning. So to consider recently viewed experiences to update the Q value. So usually when you update the Q value, you take the difference between the long-term reward, the target long-term reward, and the long-term reward predicted by the Q function. You take the difference and update that update, and that is a scalar. That is a scalar value. But in here, we're going to have a matrix of value called E. And the matrix E dimensions is state by actions. And it has the same size of the Q function. So you're going to do a pointwise operation to update the Q function using this matrix. So initially, you can see that all the values are 0 except the action that you take. So you're going to update only this value in the Q function. So it's initially it's the same as not having traces at all. Okay, so let's say that you go back on state 4 and you get a 1 in here. Then you go forward, and then you have a 1 in here now, but the previous one is decaying. And because of that, this is going to be updated as well, but with a smaller amount. Note here that the difference between the target long-term reward and the Q function is a scalar, but that scalar is multiplied by all of this. So basically you get an update on the current action and state, but also in the previous one, but with a smaller amount. So you keep going, have a new state, a new action, and that becomes your one. And this node that is decaying, and this is decaying further. So it's gonna keep going, and this is your new one. It keeps decaying, and eventually it becomes zero. So it becomes like the other. So only the recent one is like a delay learning, and keeps going. So that's how the lambda works. Okay, so now the difference between that and replacing is that in replacing, when you arrive to let's say you start with one in the same way, you have the same matrix, and then when you go into the same state with another action, that state is clear before actual putting the one in here. And then in addition to that, it's going to clip it. So you guarantee that the value is going to be between 0 and 1 because all values are going to decay all the way until 0. So that way you can have one and only one action in a given state. So you're gonna keep going and do decaying, decaying, decaying. Yeah, so I find this algorithm a little bit not that intuitive and not that effective. Let's see how that effective. It does some improvement. But I found the model-based algorithm that appears later is gonna be, it shows to be better and more simple, I think, and more intuitive as well. Okay, so for SARSA, this is the same as SARSA in the last chapter. It's going to have the same Q function creation in zeros, but notice this array. This array is the same, E is the traces array that I just showed in the image. It's the same size as the Q function. So you're going to have the same learning rates, exploration rates. You reset the environment, take the first action, apply the action into environment, get the experience point, reward, next state, select the next action, and just take it from the policy. This is SARSA. SARSA, unlike the Q learning, SARSA predicts the long-term reward, the target, using the next action, which basically Q learning is more effective because you just do the Q max. But anyway, this is SARSA. And takes the next action, and then it's going to create the scalar error, which is the difference between the long-term reward and the Q. This is the same as SARSA. And then if you're having replace states, which is replace traces defaulted to true, then you're going to clear the given state in the error in the traces matrices. You're going to clear it because you're going to put a one into it, and then you clip it just in case, although it should never go above 1. Then notice this part. The traces matrix is going to be pointwise multiplicated with the Q matrix, with the learning rate and the scalar error. So you're not only updating the current experience point, but the previous recent update, the recent seen experience points, you're going to update them as well. And notice how this matrix is going to be decayed gradually until 0. So that's basically the lambda algorithm. And the rest, inferring the Q, the value, and the pi from the Q, is going to be updated here. It's the same. Now, again, like in the previous chapter, we're going to run it, the SARSA lambda, by default, we're using the replace tracing here. And we're going to run it for over all the states and get the average, and then compare it, get the root mean square error here between the optimal value and the value from the SARSA lambda. And we're going to have the RMS also for the Q function. So we're getting the RMS for the value and the Q, and we're going to get it here. So this is the value function RMS, and this is the Q function RMS, root mean square error. So let's compare it against slippery walk 7 in chapter 6. Let's go to, I'm just going to put it here. Okay, we're in chapter 6, and we're going to compare the SARSA lambda against the plain SARSA, and both of them in the slippery walk 7. So let's go to the SARSA. Okay, so it's first visit Monte Carlo. That's not it. SARSA. Okay, so SARSA in the 7 walk slippery 7 walk 7 had 0.0467 for the value function, the error, and 0.0419. It decreased a little bit. And then for the Q, it reduced from 0.0687 to 0.06. So it did not decrease much. It improved a little bit. Okay, so now let's go to the next one, Watkins. Q lambda. So this is the same lambda improvement, but this time improving the Q learning rather than improving the SARSA. Okay, as you remember, in Q learning, we basically take the Q max. This is the same. We create the tracing matrix, the Q, everything is the same. Everything is the same until this point. So in here, again, the same. We evaluate the action on the environment and get the next experience point, use the policy to get the next action. But this is just to know if the action that you're taking is greedy or not. So you check against the Qmax and know that it's greedy. But this is, if it is greedy, then you're gonna decay the tracing array. Otherwise, you just clear it. But for estimating the long-term reward is basically getting the Qmax, as usually is done for Q learning. This Q learning as always. And then you're gonna do the same lambda stuff, but you get the scalar error between the Q and the target long-term reward. Then if you're replacing, which is true by default, you're gonna clear the current state and put a 1 into the current experience point and clip it just in case, so that it always be between 0 and 1. And then multiply in a pointwise fashion that tracing matrix with the scalar error and the learning rate to update the Q function. So this is basically the same as the SARSA lambda. The only difference is that you're doing the Q learning stuff in here to estimate the long-term reward, and if your next action is greedy, then you decay, otherwise you clear. That's the difference. Okay, so now we're going to compare this, since this is an improvement of the Q over the Q learning algorithm. We're going to compare in the 7-walk slippery walk 7 environment the Q learning versus the Q learning with lambda to see how much difference the lambda does in improving this algorithm. Okay, so here's the RMS for the value function 0.0031. Let's go and look. This is chapter 6. Let's go the Q learning. So you can see that the improvement of the lambda in the Q learning is bigger for the value function. So it's 0.0049 versus 0.0031, significant improvement. But what about the Q function? 0.0052 versus 0.007. So it got worse. The lambda didn't really do an improvement because it kind of improved something, improved the value, but the Q prediction got worse. Okay, so now let's go to the next improvement phase, which is use model learning based improvement rather than using the lambda, the traces. Now we're going with models. So model, basically in the model, you're trying to model the reward. And for that, they're gonna use a three-dimensional array. So the three-dimensional array is the R model in here. So here you're creating the Q. This is the same as any other agent. Here comes the difference. So notice that the space of this array is the current state, the action, and the next state. Given the current state, the action, and next state, what is the reward that you're getting? So it's kind of creating your own environment internally. And with that, you can create additional experiences and keep training the agent with them. Okay, so this is the same. You have the learning rate, the exploration rate. So when you enter into the loop, you're gonna reset the environment, get for the current state, get an action, evaluate the action over the environment, and get the experience point. With that experience point, you're gonna use it to train your model, your internal model. So also in addition to that, in addition to the R model, you're gonna get a T count, and the T count is the number of times a given experience point has been seen. So you have to know that the experience point has been seen so that you can use the model on it. So that's important to capture that. So you have the tuple of state, action, and next state. Okay, so you increment by 1. So you've seen that one, and you can know how many times you have seen that experience point. So then you get the difference between the reward for that particular experience point and what the model is giving you. And basically with that difference, you update the model. So you can imagine that this can be improved. If you use deep learning, this could use something like supervised learning to improve to train your model with a transformer or something like that, or a CNN, even a CNN or something like things like that. Okay, so notice that the learning rate, the more you see a given experience point, the less it's gonna have an impact on that uh, on the on the on the training of that experience point in the model. So initially this is gonna be 1, and so you're gonna have the full difference effect, and eventually this is gonna go to 0, and it's not gonna affect the update of that particular point in the model. Okay, so the other part, now we are back. This is part of the Q learning algorithm. It's gonna take the Q max for the long-term reward, the current reward, the target reward, take the difference between Q, and update the Q in the same way. This is like Q learning, nothing different. But now you augment the number of experience points using your model. So you have this end planning variable, which is number of times you're going to use your model. By default, it is 3. And you have to pick the experience point, and the way that it picks it is by using the T count. So randomly, so basically the states that from the state that have been visited, according to the count, you're gonna randomly pick one state. And from the actions that have been seen, randomly pick up one action. So this is the Dyna Q. You're gonna see later that the trajectory sampling, which is the last algorithm, is gonna improve this, the way that it takes the state and action. But sometimes this works better from the environments that we're gonna see. Sometimes taking the state and action work like this. Sometimes the trajectory sampling version is gonna be better. So that's something to keep in mind. Okay, so once you have the state and action, you can get the next state, and this is taken from the model. So you can see that the number of the probabilities, the frequency that you see the next state is going to be used to compute the probabilities, and from that you get a random choice, both with the probabilities, to pick up the next state. So basically, depending on the information that you collect on the T count, it's going to pick up the next state. And now you have the tuple. You have the state, action, and next state, and you can use that, plug it into your model, and it's going to give you a reward. And you append it here for data collection, for plotting. But then the reward is going to use for training. And then this part here is the same as Q learning here. But the difference is that the reward in here comes straight from the environment, while the reward in here comes from your model. That's the difference. The rest is the same. It's like an additional experience point that you get. Okay, so the rest is the same. Basically inferring the value function, the policy from the Q, and then run the where is the algorithm? Is Dyna Q. Run the Dyna Q over the various seeds and let's evaluate it. Again, we're still on the slippery walk environment, so we're going to compare the Q learning in slippery walk against the Dyna Q in slippery walk. So let's go down here. It's the same as we saw. And you see that that the value function has an error in chapter 6 with the Q learning, 0.0049 versus 0.0038. Okay, we improved the value function error. But also, lambda Q also did the same. But lambda Q failed on improving the Q error. The Q error for this one was 0.0052, and this one 0.0054. Almost the same. So it was a tie. It is a tie. So the model so far in this for this particular environment, the model-based version was better. Using a model was better than using the lambda. Okay. Again, like any other algorithm, those depending on your situation, the environment that you're using is the algorithm that is going to win. Not an algorithm doesn't always win in all environments. That's why it's important for the use case that you're trying to do your own experiments and do your own evaluation. Okay, so let's go to the final one, which is trajectory sampling. And this one also has an R model, has a T count like the Dyna Q. It's the same. This is the same. We are still based on the Q learning algorithm, so we're gonna train the R model in the same way. We're gonna do the Q learning in here with the experience point coming from the environment. This is the same. But then when you enter here, uh, you have a planning frequency. You configure that. But also the max trajectory depth, once trajectory depth is 100. So yeah, so you could I mean, there's a longer augmentation of the experience point. So okay, you're not gonna do anything if you don't have data. So now the difference, as I mentioned before, between the trajectory sampling and DynaQ is how you get your experience point for the model. The action, instead of being taken from the T count, is going to be taken from the Q max if you're greedy, or it's going to be taken from the policy. So once you get the action, and the state is not taken again, it's not taken from the T count. The state is going to keep in the same state that the environment gave you. So it's not going to change the state. So that difference is important. Okay, so then it's going to check, okay, for that experience point, do I have data? And if not, then keep going. You don't use your model. Then again, to select the next state, you're going to use the probabilities, the frequency of that next state, in the same way as Dyna Q. So you take the next state, now you have the tuple, state, action, next state, so you can plug it in into the R model, get the reward, save it for plotting, and then do the learning in the same way as Q learning, but the reward coming from the model rather than the reward coming from the environment. Yeah, so that's the difference of trajectory sampling. The rest is the same. Get your pi, get your value, run the trajectory sampling over all the seeds, and then get the results. Compare the root mean square error against the optimal value for the slippery walk. So we can compare against, you can see that it drastically improved the Dyna Q. So this is 0.0012. The previous one was 0. It's like 3 times more efficient. This is Dyna Q. So it's 3 times more efficient. And for the Q function error, it's 0.004 and trajectory sampling is 0.0029. So it's kind of twice improvement. So it's a huge improvement in this slippery walk. And you can imagine this also twice the improvement here and like 4 times against the Q learning. So it's a drastic improvement. And the difference is how you get the tuple to evaluate in the model that you have. And also it's more extensive, the number of points that you use for your model. That's another thing. And this model is also careful on not like the other one. You should not use the model when you don't have data on it. Okay. So now let's evaluate this in a more complicated environment. Let's go to a frozen lake, which is a 3x4 more complicated environment to see how it goes. There's a lot of details that you can see. I'm going to put the link to this in the description of this video so you can watch more in detail. Okay, so this is a 3x4. It's the same environment that we used in chapter 6. And this is the same. And yeah, so it's going to use the SARSA lambda with replacing states, with replacing traces. So the difference between this replacing traces, if you go back into a video, is basically that if you land in a state, you're going to clear the tracing matrix in that particular state. And you're going to clip it by one. That's the replacing variation of the lambda algorithm. And the counter alternative is accumulating traces, which is basically let it increase without control. So we're going to compare the two alternatives of the lambda. So you're going to see that for the value function, the root mean square error is 0.18 and the Q is 0.167. So this is 0.17 and 0.16. So it's like the accumulating version of the lambda has a slight improvement over this one. But when the lambda is used with a Q function, we're going to see a different story. Okay, so let's go to the Watkins lambda, replacing traces. Okay, so for this one, with replacing and with accumulating, let's go take a look. So with replacing is 0.0167, the value error, and this one is 0.02221. So the replacing was better in here. Let's see the Q function. This is with accumulating traces, lambda 0.0183 versus 0.137. So it's an improvement. So in the case of the Q lambda, the replacing traces perform better. So yeah, but now let's compare this Q lambda in Frozen Lake in chapter 6. So I'm gonna look for Frozen Lake in here. Okay, so we're in chapter 6 and we're comparing we're gonna get the SARSA on Frozen Lake, which is the most complicated environment that was used in chapter 6. So let's get the numbers for SARSA in Frozen Lake, and for the value function, it got 0.1915. For SARSA lambda, we're gonna use the accumulating traces, which perform better than replacing traces. Okay, so that one got 0.17, so it was a slight improvement for the value function. For the Q function, it was 0.1633. So it was a slight improvement. So I mean, the improvement is so slight that at least for environments that we have seen, it might not be worth doing the lambda. Okay, so now let's go to the replacing traces of the Q lambda. So in the case of the Q learning, the lambda function did better in replacing traces. So let's use that to compare against Q learning in Frozen Lake. So let's go to Q learning. And in Q learning, we saw that the value function is 0.0156. And here we have 0.0166. Actually did worse in the value function. In the, let's see, in the Q function is 0.0137, 0.013. So actually did worse. So yeah, the lambda in this example hasn't been proved. I guess we have to take a look at the papers, but from this example, it seems that the model-based learning is better. Okay, so now let's go to the model-based learning. Let's go to Dyna Q, and Dyna Q on the Frozen Lake. Again, Dyna Q is an improvement over Q learning, so we're going to compare these both in Frozen Lake against Q learning. Dyna Q versus Q learning. So the value function error is 0.0091, and this one is 0.01. So it's like a 50% improvement of the error of the value function. So for the Q function, is error is 0.0115, 0.013. So it's a slight improvement. So Dyna Q is an improvement in Frozen Lake. So now trajectory sampling. So in trajectory sampling is 0.006 on the value function, and this is 0.01, so it's an improvement. And the Q function is 0.0, it's an improvement in Frozen Lake. So yeah, trajectory sampling performed better in the Frozen Lake, 4x4. Okay. So the model-based approach is a clear improvement. It's a clear improvement. It's worth trying, definitely. The lambda function, I got my doubts on it, according to these numbers. So finally, let's go to a more complicated example, which is called Frozen Lake 8x8, which is basically the same Frozen Lake, but twice as bigger. Okay. So yeah, so let's get the SARSA. Let's do just the comparison. Chapter 6 doesn't use this environment, so we cannot compare anymore against Chapter 6. Let's keep now in Chapter 7, and let's compare the SARSA lambda and the four algorithms that we introduced in here. Compare them with each other. Okay, so SARSA, how it did? It did 0.1666 for the value function and 0.17 0.17. Okay, so that's pretty bad. But let's see. But he's gonna try accumulating traces and replacing traces. So let's compare between that variant of the lambda. So the accumulating traces is worse, and also this is the Q error is 0.17 in accumulating traces versus how much? Sorry, 0.71, slightly worse. But it's kind of not making much difference. If you see all the numbers between replacing traces and accumulating traces in these environments, it doesn't make much difference. Sometimes replacing traces wins over the accumulating traces, and sometimes vice versa. Yeah, yeah, but it seems like in general this might be slightly better, the replacing traces variant. So let's do the same. You cannot compare SARSA lambda with Q lambda, and the reason is because you're really comparing Q learning versus SARSA, and Q learning is way more efficient than SARSA. So what we're gonna do in Q lambda is that let's complete the replacing versus accumulating traces in the Q lambda. So in this one, the value of error is 0.051. And for Q, we accumulating traces, 0.0 is slightly worse. You see, the difference is not that much. And for Q error, in accumulating traces, 0.0683. 0.0, so it's slightly worse. So again, in these examples, we have seen that the replacing traces wins most of the time over accumulating traces, but with a slight advantage. So it seems that if you're using lambda for any reason, this might be a better approach to go. But in general, lambda doesn't seem that good. So let's compare the replacing traces of Q lambda with a with the Dyna Q, which is the model-based version. Okay, for a Q lambda replacing traces, we got a 0.051. Let's go and compare that against the Dyna Q in the Frozen Lake 8x8. A Dyna Q is over here, so we have a 0.009. So it's like a 5 times more efficient, the model-based and the lambda. Again, it's beating it again, and for the value function, for the Q function, is 0.0096 versus this one 0.00 is like almost 10 times. So in the most complicated environment, Dyna Q again beats the lambda. So, but you might think, okay, previously the trajectory sampling was beating the Dyna Q. Now let's see if the trajectory sampling beats the Dyna Q again. So 0.09 in value function versus a trajectory sampling that did bad. You see 0.0352, and for the Q error, 0.0517 versus 0.0. Yeah, so it is way smaller. So in summary, the model-based approach in these environments that we have seen has been superior to the lambda, and sometime in one occasion, Frozen Lake and the others, trajectory sampling beat the Dyna Q, but in one environment, Dyna Q beat a trajectory sampling, but both of them are model-based. So what changes between them is how you select the tuple for evaluating in your model, in the model that you're training. So yeah, model-based training is something that is intuitive, simple to implement, and effective. Lambda, maybe you can try it, but yeah, from this it seems that model-based learning and Q learning could be a good approach. But these are simple environments. Now in the next chapter, we're gonna see the usage of deep learning in more complicated environments and see what works best for the more complicated cases. Thanks.